Hi, today I'll be explaining the relationship between temperature and pressure as altitude changes. And so first we have these equations set up and these assumptions. And so the assumption is that we're using 1 mole, which will help with calculations for a specific volume, and that the system is isentropic, which means that it's adiabatic and there's no heat energy, and it's reversible, which means the external pressure is equivalent to the internal pressure. And so to get started, we can use the basic equation of statics, and we can write that down over here as dP over dz equals negative rho g. So this is the density and acceleration due to gravity. And to plug in and get this relationship, we can use the ideal gas law to plug in for the density. And with that, we have that rho equals mass over volume. And so from that, we solve for volume and then plug back in. And so with that, we have rho equals the mass and then RT over P. And then we're going to also use the molar mass to get the mass. So from this we can get rho is equal to the molar mass times the pressure divided by the gas constant R times the temperature. So that's what we have. So then we can move that up here. And arrow dP over dz is equal to negative m times p over RT times g. And so from here, we now have a separable differential equation, which we can then manipulate and then integrate it. So from here, we will move the P and T terms over to the dP and then the dz over here. So then we have T over P dP equals negative mg over r dz. And so from here, we now can integrate both sides. So we have the integral of temperature over pressure with respect to pressure. And so since it's with respect to pressure, we'll go from some initial pressure, P1, to P2. And this is equal to the, and since this is with respect to altitude and the position you're at, these can be pulled out of the integral because they are constants. So then we have negative mg over r integral from an initial position of z1 to some final position z2 dz. And then upon integrating, we can get this. And so basically all we did was add delta z, which is just the difference between the two, because you're integrating a constant of 1. And now with this equation, we will keep this in mind and then solve for temperature and plug back in later to help us get our relationship that is desired. Now that we have this, we want to solve and plug in temperature in there before we integrate this right-hand side of the equation. So to do that, we'll start off with the first law of thermodynamics, which is right here, which is a change in internal energy is equal to a small change in heat energy minus work done on the system, which is the external pressure times the change in volume. And this delta Q term is 0 because we stated earlier that the system is isentropic and that it's an adiabatic process, which means that there is no change in heat energy. So then this will equal 0. And so then we have du is equal to negative pressure, or external pressure, times a change in volume. And we can use the ideal gas law to sub in for pressure here. So with that, we have du equals RT over V, which then gives us volume, which we have here, negative T over V dV. And so then the change in internal energy is equal to the specific heat capacity at constant volume times a small change in temperature. So with that, we can go down here and we have CV dt is equal to negative RT over V dV. And with this, we can move certain variables around and then integrate. And so we'll move temperature to the left side and keep volume over here. And we'll move this here. So then we have CV over T dt is equal to there, and then that's equal to negative R over V dV. And then with this, we then integrate both sides, and this is a constant and that's a constant, so we can pull both of those out of the integral, which after integrating, we get this equation. CV times the natural log of T2 over T1 equals negative R times the natural log of volume 2 over volume 1. And with that, we can then move CV over to this side. Then we have natural log T2 T1 equals negative R over CV times the natural log of V2 over V1. And to help simplify this, we will now plug in for volume using the ideal gas law. So we'll have the ln of T2 over T1 equals negative R over CV times the natural log. So for V2 is equal to R times T2 over P2, and then all of that divided by R times T1 over P1. Right, and with this equation that we now have, we can see that the gas constant R cancels, and then you are dividing a fraction by a fraction, which then you flip. And then we have the natural log of T2 over T1 equals negative R over CV times the natural log of temperature 2 times pressure 1 over temperature 1 times pressure 2. And so what we can do now with our logarithmic properties is move this up. So it's ln of this quantity to the power of negative R over CV, and then we'll combine like terms once I erase and get more room. So now that we have more room on our whiteboard and we moved the R over CV term up, we now want to get rid of our natural logs and then just have these quantities by themselves. So by doing that, we will have T2 over T1 equals quantity of T2 over T1 times P1 over P2 to this power. And so since we have T2 over T1 on both sides of the equation, we're going to combine like terms. And by doing that, we will then get T2 over T1. And this is to the power of 1. When we move that, we get 1 plus R over CV. And this equals P2 over P1 to the power of R over CV. And then we can use this equation here of the specific heat capacity at constant pressure is equivalent to the specific heat capacity at constant volume plus the gas constant R. And so with that, we solve for R and then plug in back up here. And with that, we will then use gamma, which is the ratio between the specific heat capacity at constant pressure and the specific heat capacity at constant volume, and we will use that to simplify our exponents. So we have R is equal to CP minus CV. And with that, we then plug back in, and we will get 1 plus CP minus CV over CV. So with that, we get 1 plus CP, or we get 1 plus gamma, which is the ratio between the two, minus CV over CV, which is 1, then minus 1. And so from that, we just get gamma as our term. So then we'll get T2 over T1 to the power of gamma equals, and then we'll do the same thing on this side. So then we'll do CP minus CV over CV, and we'll get gamma minus 1 from that. So then we'll have P2 over P1 to the gamma minus 1. And with this, we are going to raise both sides by 1 over gamma so that we can isolate T2. And by doing that, we get an equation of T2 equals something. And with that, we can plug it in up here and then integrate and then get this answer for the relationship between temperature and pressure as our altitude changes. And so that being said, we raise both sides to the power of 1 over gamma. And with that, we will get T2 over T1 equals P2 over P1 to the gamma minus 1 over gamma. And then with that, we then move T1 to the other side. And now that we have this term for temperature equals this, we can plug that in and continue on. Now that we have both this final temperature equation and this initial equation that we first got, we can plug this into that and integrate. But before we integrate, we want to pull out T1 and P1 because they're known constants in this scenario. So when doing that, we'll get T1 times P1 to the 1 minus gamma over gamma times the integral from the initial pressure to the final of P gamma minus 1 over gamma minus 1 with respect to pressure. And this equals negative mg over r times the change in altitude. And so before we integrate, we're going to move these over to the right side of the equation, which leaves us with integral All right, now that we have these both moved over, we can now integrate with these two bounds. We have pressure of gamma minus 1 over gamma minus 1 over gamma from P1 to some final pressure is then equal to this. And so before we evaluate from these bounds, I'll move this term over to the right side of the equation. And then we will get negative mg r times T1 times Z2 minus Z1 times gamma minus 1 over gamma times P1 to the gamma minus 1 over gamma. So then we'll get two terms. We'll get this P to the gamma minus 1 minus this initial pressure to the gamma minus 1 over gamma, and then we'll move it over to the right side of the equation. And then once we have that, we're going to raise both sides of the equation to gamma over gamma minus 1 so that we have pressure, final pressure alone equaling something that just has our change in altitude. So that will be, have that over here. We'll have P equals P1 times 1 minus mg over r times T1 Z2 minus Z1 and then times gamma minus 1 over gamma. And we factored out the P1 that's over here. So that's just right there. And then we have this to the power of gamma over gamma minus 1. And so this equation right here solves for some final pressure with a change of altitude in it. And the same thing can be done with temperature, but I will not be getting into that.